Welcome everybody to today's lecture. Before we start, I think Robert has the presence list to pass through.
Please, as usual, just write your name on this list of attendees. And also, we would have done the homework since we had last week. Just hand it.
I haven't put it down in
Also, can you send it by email or do you have it in?
Yeah, I have something like this, but this is all not a
okay, then let's
nice
just
way.
discuss it in the break.
Okay.
Okay, and before we actually start, I also have an administrative question. How many of you have visited my Logic and Computability lecture in this winter semester, basically? Okay, and how many have been in the very last lecture where we talked about research?
I think so.
Okay, that's fine. I'm just trying to figure out if I need to find new jokes for the next lecture. Our topic for today is relation determinization, which is something that we use to go from strategies in synthesis to actual circuits. So the motivation obviously is, for the whole semester so far we've been talking about a reactive systems that interact with an environment that provides inputs and systems that give back outputs. And we have looked at the typical synthesis flow of how these things can work. And what we usually do is we start with a specification, which we then turn into some sort of game, in which we will then compute a winning region. From the computation of the winning region, you already know how you can extract a strategy. And now the last step is that we want to turn this strategy into an actual circuit so that we have a working implementation of our system that we could make hardware from, basically. So you already know about these 4 steps. This is what we have been discussing in previous weeks. So for today, we will focus on this very last step. How do we go from from the strategies to the actual implementations? Last bit that is basically missing, so that you know how synthesis of system works. So a strategy, as you already know, is basically nothing else than a very big lookup table that says if you are in this particular state and you see this particular input, then you give this particular output and go to this particular next state. And of course, this is just a very small example. In reality, these tables would be way too huge to actually write down or represent explicitly. And what we want is we want a circuit that reads these inputs and produces some outputs, and obviously also remembers what state it currently is in, and what the next state that will go to will be. So basically what we are missing is this block in between here, where we see what state we are in and what inputs we have, and determine what outputs to give and what next state to go to. So, what are we going to look at today? Basically, first I will show you a slightly different notation for games that we call edge-labeled games versus these box and circle style games that we have used so far. It's nothing very fancy, it's a very easy transformation, it just makes things a little bit easier to think about. And then we will focus on seeing how we can actually go from strategies to circuits. There's several approaches that we're going to discuss. The first one is a simple cofactor based approach. And we'll also look at some optimizations beyond the most simple version of it that you can do. Then we will have an approach that is based on computational learning, and an approach that is based on interpolation, for those of you who already know what interpolation actually is. So our learning targets are basically, you should be able to convert between these box circle style games that we have seen so far and the edge-based games that I'm going to talk to you about in a minute. You should be able to explain symbolic relations. And you should be able to explain and perform the following approaches for relation determinization, namely the cofactor approach, the interpolation approach, and the learning approach that we are going to discuss. And last but not least, you should also be able to explain the need for resubstitution during determinization, and you'll see towards the second half of the lecture what that actually means. Okay, so let's recall very quickly the notation for game graphs that we have used in this lecture so far. As always, we have an environment providing inputs and the system reacting with outputs. And we have modeled this with games that basically looked something like this. We had some states that were denoted by boxes and some states that were denoted by circles. And the rule was basically if we are in the box state, then the environment picks which state to go to, and if we are in the circle state, the system picks which state to go to next. All these edges in this graph are labeled either with inputs or with outputs, depending on whether they originate from a box or from a circle state. And this is this basically means that one time step of this system interaction here corresponds to 2 moves in this game graph. We get some inputs, meaning that we move from some box state with an input to some circle state, and then the system decides on an output and moves with this output from the circle state back to another box state. So this is a very nice formulation if you are a game theoretician, because here you have clear distinction of who chooses over what and when it is whose turn. But from a systems point of view, this mismatch where one time step corresponds to 2 moves in the game is not a very nice thing. So we want to change this in a way that one move in the game corresponds to one time step of the environment system interaction. One more thing that I forgot. Here, in such games, a strategy is basically a function or a lookup table that tells you for each circle state to which box state you should go next. And then the output that you give is determined by the game graph. If you move from here to here, you have to give output O2. That's basically it. So now here we have a slightly different game graph where basically I've omitted the circle states and the edges already represent the combined move of the environment moving first, giving some inputs, and then the system providing some outputs. So now one time step in this interaction up here corresponds to one move in our game graph. And how does this work? If we are in this state and we see some inputs, then we can basically highlight all the edges in the graph that still match this input. So for example, if we get input 1, we would highlight, this is actually going this direction. Let's say we are in this state and we get input 1, then we would highlight this edge because it's labeled with input 1, not this one because it's labeled with input 2, and this one because it's also labeled with input 1, but not this one as it is labeled with input 2. And once we have highlighted these edges, the system can choose which of the highlighted edges it wants to pick. Let's say we pick this one. That means that we are going to give output O2 and we're going to end up in this particular state. So now a strategy is basically something that says I look at the state that I'm in and an input that I'm already seeing that restricts the edges that are still available to me. I cannot choose an edge that doesn't match the input that I already see. And I'm going to choose an output which will lead me to a certain next state. You could basically say this view is more game-centered. Here we focus on the game and we just in the background somehow think that there might actually be a system that does what we do in this game, and here it's the other way around. Here we have an actual environment system interaction and the game just tracks what is going on in this interaction, if you want so. So the conversion between these two things is very, very simple. If you want to go from a box circle game to an edge label game, well, you just drop the intermediate states and make the edge labels combined accordingly. And if you want to go in the other direction, you have to introduce intermediate states, obviously for every different input that you get. If you have different inputs originating from here, for each of the different input edges that would leave from here, you would have to introduce one circle state from which then the system can choose what will go on. Okay, but other than that, there is not really a big change in what we have discussed so far, so I hope that we won't have any further problems with this notation. So let's briefly talk about relations, and in particular symbolically represented relations. By definition, when we talk about relations, we basically talk about two sets, x and y, which could in principle be equal, but they don't necessarily have to. And a relation is then a subset of the cross product of these two sets. Basically meaning that some element of the first set is in relation with some element of the second set if this pair x and y is an element of this subset of the cross product. So this might sound very abstract, so let's look at a concrete example. Let's say our sets are both the set 1, 2, 3, 4, and the relation that we are going to look at is the less than relation. So we have two sets, 1, 2, 3, 4 and 1, 2, 3, 4, and we want to determine which elements are in our relation. So first of all, we obviously know that 1 is less than 2. Therefore the pair 1, 2 is part of the set that makes up our relation. Same goes for 1 is less than 3, so the pair 1, 3 is part of our relation. And so on. I think you can see how this is supposed to work. So this is how a relation within this infix notation corresponds to a set notation where we have pairs of elements, and every pair that we have here is said to be part of the relation, and everything that we don't have here is not part. So for example, the pair 4, 1 is not in this set because 4 is not less than 1. Okay, what else do we have? In particular, of course, we will be interested in Boolean relations. So our set X will be a set of m-bit bit vectors, and our set Y will be a set of n-bit bit vectors corresponding to the Boolean inputs and outputs of the system that we are talking about. And I want to introduce two important notions with respect to relations. The first one is called completeness. A relation is called complete if there is at least one output for every possible input. Sometimes this is also called a total relation. These are interchangeable words. So for every x that is possible, there needs to be at least one y such that this pair xy is an element of our relation. And the second notion is called deterministic, and this basically says that for every x there is at most one y such that x and y are in relation. So that basically means that our relation already is a function that maps every x to exactly one y. Well, exactly only if it's also complete. If it's not complete, then for some x's there might be no pair, but if it's complete and deterministic, then we will already have a function, which is what we actually will desire in the end. Okay, so let's see how we can represent such relations. Obviously, one way to represent them is to have a concrete representation, which is basically just an enumeration of what is part of the relation, similar to the set notation that I've shown before. But when we're talking about booleans or bit vectors, we often have such a table representation where we say, okay, for the input 0, 0, we can have the output 0, 0. Or for the input 0, 0, we could also have the output 1, 0, and so on and so on and so on. Obviously, for practical reasons, this is not the best method to choose, because if we have many bits, then you already know that these will become very large, and we won't be able to hold them in memory or anywhere in the universe, basically. So what we're going to do is we're going to encode these things symbolically, which is why in logic and computability we always devote an entire lecture on encoding sets symbolically. So what we're going to do is we're going to find a characteristic function, which is a formula over these variables x and y here, in such a way that the formula evaluates to true whenever a combination is part of our relation. And obviously then it means it evaluates to false if a combination is not part of our relation. So for example, this relation over here will correspond to this formula if we do it in a very straightforward and stupid way by just enumerating every line and disjuncting all of them, and probably there is lots of things that you could simplify here, but this is not the point right now. So, for the rest of this lecture we will mostly focus on symbolically represented relations, because the formulas that represent them are usually way smaller than the actual concrete representation. One more thing, or basically let's define what the actual concrete problem is that we are given. We are given a strategy relation, which, as we now know, is a subset of the cross products of inputs and outputs. And this strategy relation describes all the allowed input-output combinations. And now to make it clear, for the rest of today, when I say inputs and outputs, what I'm going to mean is inputs and outputs to this combinational function here, that is the union of the actual inputs of the system and the state bits of the system, and the outputs are the actual outputs of the system and the next state bits of the system. So when you compare this with the actual system, we are not only looking at the primary inputs, but we are looking at everything that goes into this cloud, everything for which we need to synthesize something, which is both on the input side, it's the actual inputs and the state we're in. On the output side, it's the actual outputs plus the bits that tell us which state we will go to next. For the sake of the relation, all of these red things are inputs and all of these green things are inputs, not just the things that we call inputs and outputs here. So let's say this is a very simple example where we have two such inputs. So one basically talks about the state and one is a primary input, I think, but it doesn't really matter. And one is an actual output and another one is the next state that we are going to go to. So if you look at this is complete. So we have all possible combinations of these two inputs here, but it's not deterministic. For example, for the input vector 0, 0, we have two possible outputs. We could have 0, 0, or we could have 1, 0. Same for the input vector 0, 1, we have two possibilities. For the input vector 1, 0 and 1, 1, we only have one possibility that we can give. But it's not deterministic. So when we're given some x vector, there might be more than one y vector. So we cannot directly say we want to turn this into a circuit, because we first need to resolve these ambiguities. A circuit, combinational circuit, can only give you one particular output vector when you present it with an input vector. So what we want is, we want to find a deterministic function f that maps x vectors to y vectors that is compatible with what we have in our relation here. Meaning that it is always the case when we compute an f of x to be equal to y, then this x and y are part of our original relation. So obviously the function shouldn't do anything that was not allowed by this original relation. This is called a compatible function. So that is our basic goal. And there are some challenges to this goal, obviously, which is why we devote an entire lecture to it. The first thing is, we obviously want to find a simple function for varying definitions of simple, but one straightforward thing is it should have like a low number of combinational gates necessary to implement it. Or you can define any other metric how you measure how small or simple your function is. Doesn't really matter, it could be the depth of the gates or all different kinds of things. But you usually have some sort of metric where you prefer certain functions over others. For the sake of simplicity, let's say we focus on small implementations. That means that we kind of have to use the freedom that we have wisely. So, for example, there might be cases where if you use the freedom in a certain way, one particular output bit will always be a constant, just as an example, which is obviously very simple to implement, but if you use your freedom in a different way, then you would possibly have to look at an input bit and change the output bit sometimes, which is not what we want. The second challenge is that these strategy relations are extremely huge. You can easily think of systems with a few dozen inputs and a few dozen outputs, and if you then compute how big this table might be, you already know that this is astronomous. So we will have to work with symbolically encoded relations, which means that everything that we do, we must be able to do with symbolic algorithms. So we cannot just look at single lines of this table and say, oh, in this line I make this choice because this looks kind of very nice and so on. But we have to find something more general where we only look at the symbolic representation. And obviously we want all of this to be done very fast and very efficient, so going through all possible assignments definitely will not be a viable choice. And the last challenge that we will talk about in more detail later is that there might be some interdependence between different outputs or between different output bits, which necessitate something called resubstitution, which sometimes makes things even more complicated. So before we go into an example, let's fix some notation so that we know what we're talking about. We will use I, O, S, and S prime for the set of input bits, output bits, state bits, and next state bits, as we have most of the time so far. And as I already said, today we are more interested in the union of the state bits and the actual input bits, because that is everything that goes into the combinational circuit, and the union of the outputs and the next state bits, because that is everything that comes out of this combinational circuit. And when we use this bold type of X, then what we actually mean is the set of all possible input vectors. And the same for Y. This will be the set of all possible output vectors. Again, in this usual notation where we say it's the power set of this one, and elements present correspond to a 1 and elements not present correspond to a 0, as we discussed in one of our earlier lectures. And obviously our strategy, which we usually denote by rho, is a subset of the cross product of these two power sets, which in principle or theoretically could be represented as this very big table. And obviously in the examples that we are going to do, they will be small enough so that we can actually look at the table. Then there is one more very common simplification that we are going to look at, and that is, it is rather difficult to directly find one big function that looks at all the inputs and produces all the outputs simultaneously, which would be a function from some Boolean domain to some other Boolean domain with possibly a different number of bits on both sides. It is much simpler to compute more functions that just map to one Boolean value. So basically one function per output bit. So you first compute the function for the first output bit by looking at all the inputs. Then you compute the function for the second output bit by looking at all the inputs, and so on. By only focusing on one particular bit, it is way easier to actually accomplish this task. And basically all the methods that I'm going to talk about in the rest of today will do this in this particular manner. But as I already said with the challenges before, you cannot really compute these functions independently because there might be some dependencies between them. And we will need something called resubstitution to solve this problem, and we'll see that in an example a little bit later. Or actually, right now. Okay, what do we have here? This is the example that we have. We have two combinational inputs, S and R, and two combinational outputs, G and S prime. And our relation looks as follows. It says if the input is 0, 0, we don't care about G, but this one will be 0. If the input is 0, 1, then we can either do 0, 1 or we can do 1, 0. And for the other two input vectors, the output vector is basically fixed. So what we're going to do now is we are going to compute functions for G and S prime, and we're going to do that independently. So here we are computing a function for Fg, so we say for each of the possible input vectors we want to find a value for G, and here we say for each of the possible input vectors we want to find a value for S prime. And we're going to do that independently. So you are going to do the one for Fg, and I'm going to do the one for Fs prime. So now you tell me, someone, the values that we should put for these four question marks here. Obviously something that is compatible with what is written in the relation here.
You can use 0, 1, 1, 1.
0, 1, 1, 1. Okay, yeah, that is definitely compatible because for 0, 0 we can use a 0, for 0, 1 we can use a 1, for 1, 0 we can use a 1, and for 1, 1 we can use a 1. Okay, now I'm going to do this one, and I'm going to do 0, and for the second one I'm going to do 1, 0, 0. Let's hope I didn't make a mistake. And now let's look at the second line, the one where we had input 0, 1. And while each of the functions that we computed were correct, if we now put them into circuits and we get inputs 0, 1, then we will get output 1, 1, which is definitely not part of what was specified here. So how did this problem come about? Obviously because I just computed my function not looking at what you had already computed, and therefore I did not take into account that there is a dependency here, because basically what this light gray line here says is that if it's this input, the outputs need to be different. We don't care which way, but they need to be different. It's either 0, 1 or 1, 0. But if you look at it independently, then you say, yeah, for the first one we don't really care, for the second one we don't really care, so we could also pick something that overall is not correct. So here obviously I have done the exact opposite thing. So here I have the choice 0 here and the same choice 0 here, which leads to the same problem just in reverse. But here is also the way how we can solve this problem. What we do is we first compute the function fg, and for example let's say we have picked this one, and then we perform a resubstitution, meaning that we change our relation rho such that it is our original relation, and we say g must now be equal to what we have already picked as a function for g, which basically is nothing else as deleting all the rows that are incompatible with the choice that we have already made. So from this row, here it originally said, well, we don't care, it's a dash, but now we have fixed that g will be 0 here. So now in our new relation we will have a fixed 0 here.